So welcome everyone to the talk. I'm Saladi Rahul, and today I'll be talking about some simple multipass streaming algorithms for the Skyline points problem and the extreme points problem. And this is joint work with Timothy Chan from UIUC. Okay, so let's get started. Okay, so let me first motivate why studying multipass streaming algorithms is interesting from a practical point of view. So let's just take two examples. The example on the left shows us some data centers. So assume you want to stream data from a data center onto your local system. Right? So naturally, there will be some limited space available on your local system compared to what the amount of data that will come from a data center. Right? So that naturally motivates studying streaming algorithms. It also motivates multipass because this data is not lost, right? So it's streamed to us once, and again it is stored safely back at the data center. So we can always request it to stream it again and again for us. Right? So in that sense, it makes a natural sense to study multipass streaming algorithms. And the example on the right is similar. It's hard disks, right? So there's this big data sitting on the hard disk, and you want to stream it onto your main memory, which again has limited space. And so again, streaming is well motivated here. And then you can do multipass because you can always, the data doesn't get lost on the disk. You can always ask it to stream it again. Okay, so that motivates multipass streaming algorithms. And what happens is, if for a lot of geometric problems, if only single pass is allowed and you have a limited space, by that I mean you're not allowed to store the entire input, there are lower bounds which show that you cannot compute an exact solution for them. And for a lot of geometric problems, we really care for an exact solution. So for all these reasons, we study multipass streaming algorithms. So in this model, we are allowed to make multiple passes over the input. So that's the first condition. And the input sequence remains the same. Right? So every time it's streamed, it's the same sequence. The algorithm might exploit it, might not. That's a different issue. Okay, so what's the goal here? The goal here is to minimize two parameters. The first one is to minimize the amount of working space or the memory that we are using to solve this problem. Okay. And the second one is to minimize the number of passes we do over our data. So these are the two parameters we want to optimize. Okay, so let's move ahead. So in this work, we study two problems in the multipass streaming model. The first one is the Skyline points problem, and the second one is the extreme points problem. So the Skyline points problem is also called the maximal points problem in the computational geometry literature. So these are geometric summarization queries because the input is this huge set of endpoints and the output is a subset of them. Right? So in some sense, they summarize the data in different ways. So for the rest of the talk, we'll mainly focus on the Skyline points problem and try to explain the key ideas in the paper via this problem of Skyline points. Okay, and yeah, these two are extremely fundamental problems in computational geometry. So let's go ahead and define what Skyline points are. Okay, so it turns out cricket is my favorite sport, and I'm currently in India, where cricket is, yeah, people are crazy about it. So I thought maybe let's motivate this problem via cricket. Okay, so in cricket, there are players, some of them are called batsmen, and each batsman in this example, in the figure, is mapped to a two-dimensional point. So a batsman is considered good if his average is high. A batsman is considered good if his strike rate is high. Right? So now I mapped these 10 points here, which are 10 players. And now I have to define what's called domination. So as an example, look at point 9 and point 10. So I'll say that point 9 dominates point 10 because it has a higher x coordinate and a higher y coordinate than 10. So that means 9 dominates 10, and hence we eliminate 10 from our data set. Similarly, 7 is dominated by 5. Similarly, 4, 3, 6, and 8 are also dominated by some other points. And in the end, what remains is 0.1, 0.2, 5, and 9, the 4 points in red. So those are our skyline points. So they kind of represent the potentially good batsmen in cricket, right? So yeah, it's a well-studied problem in computational geometry, as I said. But in the last 2 decades, the database community has taken huge interest in this problem. I mean, almost thousands of papers have been written on it, on several variants of this problem. So other applications of this problem include finding best hotels, flights, and products, right? Where each one of them is mapped. In this example, it's a 2-dimensional example, but I can naturally extend this problem to higher dimensions as well. Right? And a lot of the discussion, the figures in this paper, in this talk, will all be 2-dimensional, but all the discussion extends to any constant dimension d. But the figures will be in 2D. Okay. So given this definition of Skyline and the fact that we're working in a multi-pass streaming model, the most natural idea one would have is to solve this problem would be to just update the Skyline point as each point arrives. Right? So how does that work? So let's look at the figure on the left where there are 5 points currently, which are in the red color. That's the current Skyline that we have. And now a new point, the orange point, has arrived, and it dominates 3 red points. And now on the right, you see the updated Skyline. Very simple operation. So how good is this? Right? So for some data sets, it's good. So for example, if your data is a randomly generated set of endpoints, then if you pick any subset of the points, it's a well-known fact that the expected size of the Skyline would always be, with high probability, will be order of log n. Right? So then you know that the amount of space your algorithm will occupy, in this case, will be log n, which is good. But in the worst case, it can be pretty bad, especially when the output size is very small. In the extreme case, let's assume that the output size is just 1. Only 1 point is a Skyline point, but it could turn out that the intermediate Skyline size, right, as the algorithm's executing, maybe this 1 point, which is the answer, comes right at the end, right? So the intermediate Skyline size could be as large as theta of n, and yeah. So then the space occupied by your algorithm will be theta of n, which is not good, right? So this algorithm sets the tone for what's the precise goal we have while designing our algorithms. Right? The first one is that the algorithms, we want to design algorithms which are efficient even for the worst case input. Right? Should work on all inputs. And the space occupied by these algorithms should be output sensitive. Right? So we mean proportional to h. So that's a notation here. What does h mean? H means the number of the output size, the number of Skyline points. So because we have to output all the Skyline points, our algorithm has to store these h points, right? So inevitably it has to occupy at least h space, right? So we want to design algorithms which are proportional to h. That's what we mean by output sensitive space. Okay, so with these two objectives, the next algorithm which kind of satisfies these two properties is the following very gentle algorithm. It just finds one Skyline point in every pass. Every time you perform a pass, it just finds one Skyline point. So how does that work? So look at the figure on the left, which is the input given to us. And now let's just say that in the first pass, we want to find the point with the maximum x coordinate value. Right? So you do the pass, and turns out the answer is A. Okay, good. So now what we do is we actually, as we keep finding the Skyline points, we'll actually store them in our memory. We can afford to do that. Okay, so now once we find the Skyline points, we say that some of the points have been classified. So in this case, A has been classified as a Skyline point, and points labeled B and C are also classified. All right, they're implicitly classified. We don't explicitly label them, but implicitly they have been labeled as not being skyline points. Right? What do I mean by implicit? Because we are storing this point A, so anytime, but we won't store B and C, but anytime they are streamed again, we can always check it with A, and we can clearly see that, oh, A dominates B and C, so they're not skyline points. So yeah, so A, B, and C have been classified. So then what we do is, in the next pass, among all the points which have not been classified yet, we find the point with the maximum x coordinate value, right? So in the second pass, we find the second orange point, right? So like this, in every iteration, among all the points which have not yet been classified, we just keep finding the point with the maximum x coordinate value, right? So very simple algorithm. So how much space does it occupy? Because we only store these skyline points, the space occupied is order of h, and the number of passes is also bounded by order of h, right? So this is good in terms of space, since I said we have to anyways output h points. Right? But in terms of passes, it's not good, because you really want to do better than just finding one skyline point in every iteration. Right? So especially when h becomes quite large, yeah, this is not good. Okay, so now we'll present an algorithm, a randomized algorithm by Das Sharma et al. And we'll go into some details about this algorithm, because our final algorithm will actually use this as a subroutine and actually improve upon this. Okay, so we'll assume that the value of h is known. H is the number of skyline points. It's easy to remove that assumption, but we'll just assume it's known to us. And then we'll perform an iteration. An iteration is defined as having two passes. And what happens here is that in the first pass, we'll compute a sample of the input points. So P is the set of input points given to us, and we'll compute a sample, capital R, of size R. And the value of R will be revealed later. And so how is the sample constructed? It's every point is visited independently and uniformly at random with probability R over N. It is sampled. So you have this bunch of points, and they are shown in red in this figure, right? I mean, the 4 points corresponding to the row of R, and those are, think of them as our sample. And now in the second pass, what we want to do is a crucial step where we want to update this R to a new set called R plus. So specifically, if there's a point in R, which is already a skyline point, then we won't touch it. It will remain as it is and kept in R plus as well. But if there's a point in R which is not a skyline point, then there could be at least one or more than one point, one skyline point which dominates it, right? So in the second pass, we'll try to find one such skyline point which dominates it and put that in R plus. So eventually when we reach R plus, all the points in R plus should be skyline points. That's crucial for our analysis. That's why we want to do this second pass. Okay, so actually, yeah, so it's not that difficult to construct R plus. There are basically 3 cases which arise. So that's what I'm illustrating here. If we look at the case A, which is the most interesting one. So again, these 4 red points are the set R. And actually this set R is stored in memory, right? So that's why we are talking so much about it, right? So this set R is stored in our memory, and again, this R plus will also be stored in our memory. So now in the second pass, some point cross, which is shown as a cross, has arrived, and it actually dominates 2 points in our set R. So then what do? We just discard these 2 red points and then add this cross into our memory, right? And what we get is what is shown in the bottom figure, where the remaining 2 red points survive and this cross also survives, and the algorithm proceeds. And the other 2 cases are, let's look at case B, where a point arrived, which again shown as a cross, but that itself is being dominated by one of the red points. So clearly a cross cannot be a skyline point, so we just discard it and nothing changes in our memory. Similarly, case C, We see a point shown as cross which has arrived. We don't know anything about it. It could be a skyline point. It need not be a skyline point. It's hard to infer just by looking at direct points. So we just again discard it, and again nothing changes in our memory. Right. So these are the steps. So in the second pass, every point comes one after the other. It falls under one of these three cases, and accordingly we perform an update step. And these are the two claims which come out of this operation. The first one is that all the points in R plus are indeed skyline points. You can trust me on this. Maybe it's not completely obvious why this should be true, but if you just spend a few minutes, you can just figure it out. And then we didn't talk about the sample size, right? So what Das Sharma et al. Claim is that if you choose a sample size in first pass of size order of h log n, then in expectation, the number of points that are classified by R plus is greater than or equal to n over 2. So to remind everyone what classified means, so we have this set R plus. So all the points in R plus are classified, right? They are skyline points. And all the points that these R plus dominate, they're also classified. They are non-skyline points. So the claim here is that the number of such classified points by R plus is greater than or equal to n over 2 if we choose the sample size of h log n. Right? So now this now tells us why the number of passes, why order of log n passes is enough to finish the algorithm, because in each iteration, the number of unclassified points falls by a factor of 2. Right? So after log n iterations, you are able to classify all the points, and in order of log n passes, we are done. Right? So in summary, what Das Sharma et al. Do is they use their algorithm uses h log n space, and the number of passes is log n. And now the crucial contribution in our paper is that we are able to improve upon their space complexity. We don't need h log n space. We claim that order of h space is enough. Okay, so what is our algorithm? It's actually a very simple twist to Das Sharma et al.'s algorithm. Right, so before that, so basically there are two cases to our algorithm. This is the first case, which is shown here, which says if the number of skyline points is very small, that is h is just order of log n, then we don't have to do anything fancy. Just run a simple algorithm that I described before, which finds one skyline point per iteration. Right? So the space occupied by that algorithm was order of h, which is great. And the number of passes it performs is order of h, which is okay in our case because h is anyways order of log n. And so in number of passes is still within our bound of order of log n. That's what we are targeting. Right? And now the second case is h is at least log n. In that case, we say we just run Das Sharma et al.'s algorithm. That's all. But with one crucial difference. So in their case, the sample size was h log n, but now we are saying you don't need a sample of h log n size. You just need a sample of size order of h. And that's what is capital R here. Right? So that's the crucial difference we're saying. We're saying you don't need a sample size h log n. And because of this, the R space actually comes down to order of h, and the number of passes will be log n. So these bounds hold with high probability. And the key lemma that we prove here is similar to what they prove, is that in each iteration, that our algorithm is essentially still Das Sharma et al.'s algorithm. So remember all the R and then converting that to R plus. So that was one iteration. So the number of classified points is at least n over 2 with high probability in each iteration. So that's true even with the smaller sample size is our claim. And the nice thing is for proof is it's way simpler than the proof that Das Sharma et al. Had. We could really simplify. They had to look at several cases, actually 2 cases. Heavy, light, bound the expectation of each one of them. we overcome all of that. So let me just give you a brief sketch, not give the finer details of our proof, but it's can essentially be summarized in one page. So I'll just give a brief overview. So some notation here. So let S star be the skyline points of our input set, right? And let's pick a subset of these skyline points and call it set A. And set A is actually a bad set. By that we mean, look at the definition. A is a subset of the skyline points such that the number of points classified by A is less than n over 2. Right? So if you look at the figure on the left, there are 5 skyline points, but our set A is these 2 points in orange, and the number of points that they classify is shown in those shaded rectangles, right? And that's less than n over 2, right? And we call that a bad set. So now remember that this update algorithm, right, which updates R to R plus, right? What we want to understand is it possible that our algorithm outputs R plus to be equal to A? If it does that, then it's not a effective iteration, right? Because we didn't classify at least n over 2 points. We're classifying less than n over 2 points. So it's a bad event. We want to understand how likely can that happen, right? So we want to bound the probability of R plus being equal to A. And it's actually a very simple calculation to show that it will be bounded this way. And again, we use the fact that our sample size is order of h here to do the calculations, right? And then, so how many such bad sets could be? We just trivially upper bounded by 2 to the h, which is basically all possible. Yeah, R S star, right, is actually h. The size of it is h. So we just look at just simply upper bounded by 2 to the h, right? And then this is the bad event E. Right? At the end of the iteration, the number of points classified by the algorithm is less than n over 2. Right? And computing that is actually a simple union bound over all possible bad sets A. Right? So if you just do the math and use the fact that h is at least log n. So this is the reason why we had these two cases of handling small values of h and large values of h, because our analysis only goes through if you use this fact that h is at least log n, then you can show that this bad event can occur with very small probability. Yeah, so it can just basically be summarized in one slide. Okay, good. So moving on. So let me just summarize a few more things about our algorithm. So the figures were all in 2D, but it actually works for any constant dimension D. Also, our algorithm can achieve trade-offs. So the one presented there said the space was order of h. Actually, if you can, and the passes was order of log n, but you can actually get down the number of passes by bumping up the space, right, for the parameter b. And that's how it looks like. So that's nice. In fact, we have another algorithm in our paper which does slightly better than log n passes. So, but the bounds hold in expectation now. So the expected space will be order of h, and the expected number of passes will be log h plus log n over log n, ever so slightly. So when h is small, yeah, we do see some improvement. Okay, good. So that's all I had to say about Skyline points. In the second half of the paper, we actually use the same framework and actually study the extreme points problem. I'll just briefly go over the results. So what's the extreme points? So in 2D, it's very easy to define extreme points. You're given a bunch of endpoints, you compute their convex hull, and all the input points which you see on the convex hull here on the left, right? The ones in black discs, those are the extreme points, right? And the crosses that you see are not the extreme points. Well, in general, in a d-dimensional space, the formal definition is on the right. So you compute the convex hull of your input set P, and then you pick a point P in that input, remove it, and then again compute the convex hull on the remaining points. If the convex hull changes, then P is an extreme point. Right? So there is some facet on which P lies. Okay, good. So it turns out that in 2D and 3D, the number of extreme points and the number of facets are proportional to each other, but it's no longer true beyond 3 dimensions. Right? So here we want to study the extreme points problem. So this problem was already studied in 2D, right, by Chan and Chen, and they gave an, again, H here means the number of extreme points, right? The same as the Skyline points. And so they came up with an algorithm which uses H log square in space and log square in passes. Very recently it was improved, where the number of passes, they could get it down to log n, right? And these algorithms can actually be extended to 3D as well, but they don't extend beyond 3D, right? And there are several NH times non-streaming algorithms, right? The algorithms which basically work in main memory. Many of them have been proposed, classical convex hull computation algorithms. But the problem is they are inherently sequential in the sense that in every iteration, they'll only find one extreme point. So again, the number of passes have to be at least H in that case, right? So what do? We again use our framework that we have built for Skyline points. And of course, we have to combine that with some additional machinery of using linear programming, right? So to find these extreme points. So using that, the passes is log n, and the space is proportional to H. There are some log factors which have been attached there, right? So again, this works for any constant dimension D. So again, I mean, what we do is we run, we pick a sample, and then we try to run many linear programs parallelly and try to find several extreme points in each iteration. Okay, and then we actually have a lower bound as well, but that's for a more general problem of finding maximal points in a poset. And we kind of show a lower bound saying why randomization is needed for all these problems. If you only stick to deterministic algorithms, you might have to spend at least H passes. So the adversary can create such a setting. So it's a nice self-contained proof we have. Okay, so in conclusion, let me finish by posing two open problems. So in this paper, we only talk about upper bounds. What about the lower bound? Right? How good are our upper bounds? It's a natural question. So coming up with randomized lower bounds for Skyline points problem, right? That's a big open problem. So it would be nice to compare the upper bounds and lower bounds and see, can come up with an optimal solution. And for the extreme points problem, there, as I said, there are a lot of logs hanging in there. Can you shave them off? Okay, thank you. Thanks for listening. Bye.